everybody. Sorry for the long gap in between making videos. It's just with school and work, it's been hectic trying to make anything. But I have had an idea on the back burner, and it's this one, and I wanted to end the year off right by giving you a notation analysis video. In specific, I kind of wanted to bring a discussion about over the trigonometric functions, or rather the way we commonly write them. In specific, I'll just write it out. Sine of x, cosine of x, and tangent of x. They have some ambiguities, or rather they have some openness for misinterpretation. I'll give a few examples right now. So imagine, if you will, for the case of sine of x, and possibly even for the case of cosine and tangent, imagine that we just had some kind of solenoid, right? And it's a finite length. Maybe we can call that length L. It's arbitrary. It doesn't really matter in this case. But an arbitrary length L solenoid might actually have some number of loops. Crazy to think about, right? So that number of loops might be denoted by the number or letter n. And that'll pop up in some relationship, right, n. And then so you might say, well, what if I wanted to indicate radial position? Sometimes people will indicate radial position with just the letter s. And the reason being is because sometimes you'll have a position vector, r vector, pointing to somewhere else that's not necessarily radially outwards. And so that position vector is way more commonly denoted as r vector. And so the r vector, if you look at the magnitude, that's going to be equal to just regular old r. So typically just the radial component in the xy plane with z equal to 0, that's going to have a value of s, or be denoted as s. So that's where you might see s in the sin of x pop up just on its own with just some radial component in the xy direction. So the I, where might I pop up? Well, that's common. That's I is equal to square root negative 1. And so if you combine all of these together, you have the square root of negative 1. Maybe you have some radial component s. Maybe you have the number of loops of a solenoid. Oh, heck, and why don't we multiply it all by the x component of all of that? Oh, would you look at that? We actually have sine of x. And if you weren't careful about how you set anything up, or careful in the fact that you weren't just looking at this part of the relationship, which is clearly sine of x, you might actually be led to believe that you have a trigonometric function, and therefore that this is some kind of argument, and this is exactly what you learned all those years ago, maybe. But it's not. It's clearly not, because the square root of negative 1 is not involved in sine of x. That's not part of the definition. And so you can see how sine of x, or sin, argument x, or parentheses x, is just open for misinterpretation if you take the explicit symbols too literally. But isn't that what we do in mathematics, in a sense, right? We kind of use explicit notation to guide us in understanding areas of maybe our logic that we don't necessarily think are logical right off the bat. And so I guess with this as our motivation, that's where we're going to start talking about, I guess, how do we solve this problem of notation abuse, or notation ambiguity, if you will. However, just to strengthen our argument a little bit more, let's maybe play around with tangent of x, and just to see how that could apply and how that could arise. Well, what if we had some kind of, some kind of little particle, and it's moving around in some kind of fashion where it's repeating some kind of wavelength with respect to some time period. So some time period, delta t, we'll call it t final minus t initial. Well, if we start the clock at some time that we define as 0, time initial equal to 0, we'll have a 0 on our right-hand bit, and for t final, imagine that we ended at some final time t, so that's just going to be the variable t, and so then we'll have delta t equal to t. So there you go. Now we have a change in time for a particle moving in some fashion over some with some wavelengths, and it's operating over some time interval of t. Okay, so t is popping up on its own as some time period. Great. Now, what happens if n is the number of wavelengths, or the number of integer wavelengths that fit in this particle's path? So we have 1 there, we have 2 there, and then maybe you have 3, and so on and so forth. And so however the number of wavelengths we have, that's going to be equal to the number n in this case. And so what about a? Well, what about if a is the Bohr radius. Yeah, Bohr radius comes up a lot in nuclear physics. And the Bohr radius is actually a constant number. It is some number that we do know. And so we would say that the Bohr radius is A, and that the number of wavelengths of this particle in oscillation, that's a number N. And then we have the time interval in which it does all of these actions, or rather it undergoes its entire path's journey. And this is, again, T. And so what happens if this is maybe in some X, Y, Z coordinate plane, right? And then this is going to have some X component. So you throw that all in there and you end up having delta T times A times N multiplied by the X component. And you have X, but that's equal to tan X. Again, notation abuse or notation ambiguity. Now, how do we solve this? So let's look at the solution. However, in doing so, I think it's appropriate and more so just respectful to kind of give credit to the first person who founded this idea, or rather motivated this idea and what we're about to talk about. And that's Richard Feynman. Many years ago, Richard Feynman approached this idea of ambiguous sine, cosine, tangent definitions and replaced it with what we call Feynman trig notation. It's not popular or rather super widely known, but it is known. And Feynman, let's write it out, Feynman trig notation is a really nifty way of writing sine, cosine, and tangent in ways that are not open for misinterpretation, and they are very direct and actually representative, or rather indicative, of something called generator function notation. Now, we can get into that in just a little bit, but for right now, we're going to focus primarily on what exactly is this new notation. Well, Feynman trig notation is basically as follows. This new notation, given by this loop-looking root, almost loop root. That's sine of x, defined to be sine of x. This is the new notation, and you can notice that left-hand operator, rather that left-hand function notation, is very clear. There is nothing in our mathematics nor our physics definitions that looks like that, and therefore it is unmistakable that will be sine of x. Similarly, we have cosine of x, and that's given by this new notation, which is cosine of x, and tangent of x, which is given by this tangent of x. And for those curious-minded, you're probably going to be wondering about the cosecant, secant, and cotangent, and that's actually funny. It's given by the reverse. So this is going to be defined to be cosecant of x, and this is going to be defined as secant of x, and this last one is cotangent of x. Now, all of these unique notations are very clear in what they represent. There is no misinterpretation here. And you can see how if you were to write this, you would not be able to pull out square root -1 or some radial s component s or some number of loops n from that relationship on this left-hand side. It's just not really possible. It's not there. The explicit writing of what we've written down, sorry for the redundancy in my statement, but yeah, the explicit notation of what we've written down does not give indication for any of what we previously said we could find, which was s, n, and the square root -1. That being said, this basically solves a problem. Now, great, it's all well and done. We have new notation, sine, cosine, tangent, cosecant, secant, cotangent. It helps us. Is there anything else what was the motivation for this conversation, Daniel, right? Well, have you considered the exponential function? Most haven't, right? Most people usually choose to write exponential function as some e to the x, maybe, or some people will choose to write exp of x, and ooh, do you see that? Exp of x. Do you see how sine of x, cosine of x, tangent of x, all the fun ones? They were all written with their three-letter ambiguities. And that's what our topic of conversation is today. Let's create some new notation, yeah? let's create a new exponential generator function notation, the Valle notation. And let's use it to actually give more indication of what this function means and how it can be used mathematically. So that way we don't have discrepancies in the future when we're deriving something new, yeah? Okay, let's start it. Let's try it out. And what better way to start than to literally just define the symbol outright? So the symbol we are going to use for our new exponential function notation, rid ourselves of ambiguity, is going to be as follows. It's going to be kind of like an E, kind of like a weird EMF from electrodynamics. And it's going to be kind of like what we did before with the root. And it's just going to be of x. That will be defined to be the exponential function of our argument x. We rid ourselves of ambiguity, and it looks kind of fancy. I'm not going to lie. I've played around with the idea of using hearts and heart of x, just because I literally have wanted to bring more love into physics. I always say that the sciences don't have enough love, enough emotion. I think it's nice. I think it's cool. But either way, it doesn't work because it takes a long time to write. I feel like the E is a lot faster and actually makes probably a little more sense with, exponential and you got an E in front. That makes sense. Okay, cool. We'll work with it. So for our purposes, we will define the exponential function of x to be this new notation, E of x, if you will. Now, I did make note of something, like I've said the word multiple times already, generator function. What does that mean? I think it's important to kind of cover that idea because or else saying it has no weight, right? So let's cover it. Let's talk about what is a generator function. So a generator function or a generating function in a mathematical sense is something that encodes an infinite sequence of numbers and kind of helps them, like you rally them up or corral them in some kind of power series or some kind of Taylor expansion, if you will. That's the mathematical way of saying things, and it's really cumbersome to say it and even kind of take it in. So why don't we just kind of break it down in brass tacks, right? So you may or may not remember, but from Calculus 2, whenever you have any function f of x, typically it has, I think it just has to be continuous and differentiable, if I remember correctly. But whenever you have some kind of function f of x, which is, we can assume it to be continuous and differentiable, you can find that it has a power series expansion, or they call it a Taylor expansion oftentimes, because I think the guy had a last name Taylor, and he found this. So, yeah, you can center it at some point A by taking the nth many derivatives at the point A, and you're going to take x minus a to the nth power and n factorial on the bottom. And if you just run the series on this infinitely, you'll get a Taylor expansion. And you might remember that Taylor expansion looks something like f of a plus maybe f prime of a, x minus a, and then you're going to have 1 factorial plus da 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 da. My whole point in drawing this out is that if you notice, there is x to the 0 here. You have x to the first power, and if you kept going, you would have x squared followed by x cubed, da 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 da, in each term. But that's going to be something that looks like a n x to the n, where you have a sum from n equals 0 to infinity, such that a n belongs to the real numbers for all n. The reason I write this is because an is just some constant, whereas f of a, f prime of a multiplied by negative a and the 1 factorial, and you do all the mess and the manipulation, but you're really just going to have a power series, a n xn. You're really just going to have a bunch of constants with a bunch of powers of x, and that's going to be a good approximation of your function. Now, this approximation of your function, or this Taylor series, is actually a way of saying generator function, or it is a generating function. You're generating an infinite sequence of numbers, coefficients a0, a1, a2, a3, and up to infinity, a infinity. You have an infinite sequence of numbers represented formally through a power series, or as constants in a power series. Why is this so important? Well, it's more so, it's not necessarily important to just regular old kinematics, or like if you're just doing maybe projectile motion, you have a cannonball shooting out at some velocity, and you're like, oh yeah, I gotta consider generating functions. Definitely the thing I gotta do, right? That is not like typically how this arises. It's not, it's not in everyday physics, let's say it like that. What it does start to arise in is once you start to kind of get to modern physics, and when you have to, or rather you'd want to start to consider, energy decay, or rather wave functions, and all the cool stuff of modern day science. Modern day science kind of demands that you use something called a Hamiltonian operator, and it just so happens that this operator needs to be shoved into an exponential, or rather, it doesn't have to be. But we've done it this way, and it works very well. And so typically you'll have an exponential function, and you'll have negative I h hat, which is the Hamiltonian operator, multiplied by some time, or rather divided by h bar. And you're going to say, well, how the heck is there an operator inside of the exponential function? How is it? And mind you, the Hamiltonian operator, it can be represented by matrices. Maybe it can be, and even just saying that, let's stop there. Like, what is a matrice inside of an exponential function? What does that mean? Like, I always like to say that, but that's the idea. Is like, what does that mean? And so this is where this exponential generator function notation is going to start to come into play, because now that we have this idea of this very explicit e to the x, or rather e of x, we can kind of say, well, the argument of this exponential is, for the bottom one, is negative I Hamiltonian times t over h bar. So what we're really asking is that if we have a generator function in taking some argument which happens to have an operator, what would that look like? Well, it turns out, and it's super extraordinarily simple, because if you have e to the x, you may or may not remember, once again, that it has an explicit power series expansion or Taylor expansion, using the formula from above of the fa x minus a to the n. If you do all that and you center it at 0 and you do the necessary work for the exponential function, you're going to get x to the n over n factorial. Now, the interesting part is that if you plug in the Hamiltonian into this argument, you're going to see it happen naturally. Rather, if you plug in that whole mess that we had above. So let's do it. So we have exponential generator function notation on it. Negative I h hat t over h bar is equal to the sum, n equals 0 to infinity. And then the argument for the x is going to be negative I Hamiltonian operator t over n over, oh, that's wrong. Sorry about that. H bar. That's the nth power over n factorial. Now, the only thing we're going to be concerned with is because, well, if we write this, you're going to notice that we have equals. Let's just keep going. We have n equals 0 to infinity. We're going to have negative I t over h bar. That's going to be to the nth power. That's simple. You're just going to run it. It's not that it's simple, but it's like the I is going to flip every time you have n as even. You're going to have I squared. So then you're going to have a negative 1 pop out. So you're going to have a maybe alternating negative, positive. So it's not necessarily that I understand it. I'm saying it's simple in terms of what the pattern is going to be. But what I'm saying is that it's simple, and that stuff, negative I t over h bar, that's stuff that we can evaluate. That's stuff we can figure out. But what is going to be tricky is this Hamiltonian operator to the nth power. What is that? Well, I guess that takes understanding what an operator is, right? So when we typically think of operators, well, we've been using them, and maybe we even think of the derivative operator or an integral operator. So whenever we have any derivative operator, right, we have the derivative with respect to time, and then I have it to the nth power. Isn't that really the derivative with respect to time times the derivative with respect to time times the derivative with respect to time continuously n amount of times, right? So isn't it the same thing for the Hamiltonian? It is. And so that's the beauty of this, is that this Hamiltonian operator to the nth power is really just a Hamiltonian operator applied singly, but just n amount of times. And you're going to just get some amount, n amount of times. So the motivation, again, was ambiguity in sines, cosines, tangents, and it leads us to wanting to talk about a solution for such ambiguities. Richard Feynman comes along and he gives us the answer, and he says, Feynman trig notation, this is the way we're going to do things, and it's going to make our math simpler. And if you actually go back and if you've been doing quantum mechanics and you remember how much it came up, sine, cosine, every time we try to normalize wave functions, and especially in 3 dimensions, it happens so much where you're just constantly writing sine, cosine. It's just so much that, hey, why not write it so much smaller? I mean, come on. If you're literally writing sine so much, sine of x, why wouldn't you just want to write a little loop and an x like that? So clean, so simple. And if you're really writing exponentials, do you really want to write exp of x every single time? Why don't you really want to just write a little loop and then an x? There you go, exponential of x. I didn't write it good there. I'm writing fast, but that's the idea, is that it's small, it's simple, it's convenient, it's saving time, something we can't get back. So that's the motivation for this. That's the whole idea. The motivation, or rather the byproduct, is that, now we get to talk about generator functions more cleanly, because most people are unaware of like the sine of x, cosine of x. They also have series expansions, which I think I'd urge you to look up and say, what is the Taylor expansion of sine of x, or what is the Taylor expansion of cosine of x? And you'll see that they do have similar series expansions, similar to x to the n over n factorial for the exponential function. And the same rules apply for applying the Hamiltonian or any kind of operator a hat and inside those functions. I guess the path is just more clear now, right? So with all of this being said, I guess that wraps up our conversation. It's already been about 20 minutes long, and I guess we will definitely save our conversations for another time about maybe how we can apply this and how we can kind of really see a new notation arise from, well, I don't want to write this exponential times negative exponential function of negative I h hat t, but over h, it's literally cumbersome. It's annoying. And if this comes up all the time, I'm going to find a new way to write that too. So yeah, I did that too. And it actually makes the notation and the derivations so much cleaner, and it looks so nice, and it makes 3 pages into one, and I'm happy. And I just want to share that with you. So yeah, I'll save that for another video. But for now, I hope this helps in some way. And I hope your maths or your physics or your sciences or even just your days and your months are going great and go amazingly. And I will definitely try and make another video soon and see you guys another time or talk to you guys soon. Until then, have a wonderful life. Like I said, enjoy your days, and Valle notation. Spread the word. Bye.